Today's lesson is on theorems about roots and zeros. I'm going to remind you how to factor. We're going to then find all of the roots and zeros. We're going to check to see if things are factors. So here we go. When there are four terms, we need to factor this. We'll factor by grouping. When we tried that, we got factor out an x squared. You're left with 6x plus 11. When you factor out a 1, you're left with 6x plus 1. So notice that the parentheses are not the same. We can't factor it out. Thus, we need to use a different method for factoring. We're going to use long division or synthetic division. I prefer synthetic division because it's much faster, much easier. So we're going to use the remainder theorem, the factor theorem, to do this. The remainder theorem is when a polynomial is divided by x minus c, the remainder is equal to f of c. Or in other words, if we were to plug in c, we would get the remainder at the end. Factor theorem is very similar, saying that if we plug in c, we get 0 instead. Then x minus c is a factor of f of x. So we want to determine if the following is a factor of f of x. So we'll try x minus 1. So as I set up synthetic division, I would put a 1 inside the box. Remember, I need to represent every power all the way down to the constant. So I have a 5, a negative 2, a negative 4, and a 1. First number drops, multiply the 1 to the 5, that's 5, and then we add these things together, we get 3. So 1 times 3 is 3, add these together, you get negative 1. 1 times negative 1 is negative 1, add these together, you get 0. Since we got 0 as our remainder, x minus 1 is a factor of this polynomial. So we would write the answer as x minus 1, and then we have 5x squared plus 3x minus 1 as our other polynomial. Alright, now let's check to see if x plus 3 is a factor of this also. So I would put a negative 3 in the box. I would have 5, negative 2, negative 4, and 1. Drop the 5 down. Multiply, you get negative 15. Add them together, you get negative 17. Negative 3 times negative 17 is positive 51. Add these together, you get 47. Negative 3 times 47, that's negative 141. Add those together, you get negative 140. Notice that the remainder right here is not 0, thus this is not a factor. When it's given to you like this, a polynomial, and then it tells you what c is the thing that goes in the box. We do not have to change the sign nor solve for 0 like we did in this case or this case. We only have to put the whatever numbers right there in the box. Now again, remember that we have to represent every single power all the way down from the highest down to the constant. So 6, x to the 6th is 3, x to the 5th is 0, 0, 0. Then we have negative 10x squared This is the x spot, so we got negative 4, and then our constant of 3. Negative 3 times 3 is negative 9. Add them together, you get negative 9. Negative 3 times negative 9 is 27. Add them together, you get 27. Negative 3 times 27 is 81. Negative. Add those together, you get negative 81. Negative 3 times negative 81 is 243. Add these together, you get 233. At this point, can you see that this will not equal 0? So therefore, it will not be a factor of f. This number is just getting larger and larger. So this would be 699. Add them together, that's 695. Oh wait, negative, sorry. That would then be 703 negative. So this just keeps getting bigger and bigger. This is not a factor. Alright, with factors, they don't always give you the factor. You will have to factor it completely yourself. So there's a way to do this, a way of obtaining a list of useful first guesses when you are trying to find the zeros of a polynomial. Given a polynomial with integer coefficients, the potential zeros are found by using this method. Take the factors of the constant divided by the factors of the leading coefficient. So for example, if we had something like 5x to the third plus 8x squared minus 2x plus 12, we would write the factors of the constant, which is this one over here, 12. So that's 1, 2, 3, 4, 6, and 12. We divide that by the factors of the leading coefficient, which is 5, 1, and 5. And then we would write all possible fractions with this problem. So if we took all these and divide them by 1, all of them would have plus or minus. So I'm just going to write it once in the very front, plus or minus 1, 2, 3, 4, 6, and 12. And then we'd have all of these numbers divided by 5. So 1/5, 2/5, 3/5, 4/5, 6/5, and 12/5. These are all of the potential zeros for this polynomial right here. Alright, so on this problem we want to list potential zeros. Again, we take the factors of the constant, so that would be 1, 3, 5, and 15. Divide them by the factors of the leading coefficient, which are 1 and 2, which means we could have a plus or minus 1, 3, 5, 15, 1/2, 3/2, 5/2, and 15/2. Here's another example. Again, we would take the factors of the constant divided by the factors of the leading coefficient. So the constant is 1, 2, 5, and 10. The leading coefficient would be 1, 2, and 4. So dividing all of them by 1, we would have a 1, a 2, a 5, and a 10. Dividing them all by 2, we would have 1/2. That would become 1, which we already wrote. 5/2, and then 5, which we already wrote. Now divide them all by 4. We have 1 over 4. Then we'd have 2 over 4, which is a half. We already got that. We'd have 5 over 4. And then we'd have 10 over 4, which is 5/2. We already got that. So here are all the potential zeros for our function. Now, how do you actually find the zeros and factor all of it? Again, that goes back to the very first problem that we looked at. Say we have 6x cubed plus 11x squared plus 6x plus 1. we would have the factors of 1 divided by the factors of 6. So we'd have 1, 1/2, 1/3, 1/6. Plus or minus all of these. These are the numbers that we would put into the box for synthetic division. Now, I can see that all of these are positive, which means I need to multiply by a negative so that I can subtract from these numbers. So I'm going to ignore all of the positives and just use a negative. I'll start with -1. -1 times 6 is -6, I get 5. -1 times 5 is -5, add them together, I get 1. -1 times 1 is -1, add them together, I get 0. Thus, where x equals -1, that is a 0, so I would write that as a factor of x plus 1. Now I could factor this remaining, which is 6x squared plus 5x plus 1. Or I could continue on with synthetic division, and I'm going to use that here. Now I try -1. If I tried -1, that would be -6 makes -1. -1 times -1 is +1, which makes 2. That's not 0. It won't work. And I know that it has to be negative because all of these are positive up here. So I can ignore all the positives, and I tried 1, which means now I'm down to my fractions. So I'm going to try -1/2. So half of 6, that's 3. Add them together. Half of 2, that's 1. Add them together, I get 0. So that means x is equal to -1/2. So I would write a factor of x plus 1/2. Now I'm left with this 6x plus 2. Most of the time you do not have fractions in your factoring. So I could factor out a 2 from this factor here, leaving me with 3x plus 1. And I could take this 2 right here, and I could multiply it into this parentheses to make it 2x plus 1. So the factoring for this polynomial would be x plus 1, 2x plus 1, and 3x plus 1.